So where we left off, okay, we were doing last time control volume analyses on the different components. So we looked at momentum, energy, and mass. And we're doing control volume analyses on all of these. We're able to derive the Navier-Stokes equations and the energy equation for general circumstances, right? We're going to now today take the equations that we derived and plug them in or apply them in a boundary layer situation, and then see what happens to the equations and how they can be simplified. So more derivation today, but I think maybe this is a good chance for you, if you haven't seen it before, to see how you arrive at these simplified equations that ultimately you just sort of pull and use. But if you know how you got to them, then you know when they're not valid, right? And that's really important. So, okay. So today, let's start with this simplification of the continuity equation. The first thing that I want to do, I'm going to use Top Hat, so maybe have your phones ready in a minute here. But first I want to remind us of what we're looking at. So we have this conceptual model again of how heat transfers into the fluid as it flows over a plate. So when you're thinking about this, think about, imagine that you have some well-insulated, very thin plate, right? And it's positioned vertically. And you take that plate and you put it, it's at constant temperature T infinity, and then as soon as you hit x equals 0, it comes in contact with this heated surface. So think about what happens to heat as it sort of conducts up into that plate as it's moving along. Right? That's our conceptual model of heat transfer in fluid flow. We're essentially saying that there's these little differential columns of fluid that are accepting heat that's conducting into it. And we're modeling that according to this approximation. Okay, so the approximation says, yeah, if we have some component of time, which we've modeled as velocity or position over velocity, then we can say that the growth of the boundary layer corresponds to that sort of approximate relationship. So the question that I have for you in Top Hat is as follows. Let's see, so thinking about this model, let's look at the question here. So the question is this. So the question is, will the approximate model of boundary layer growth, delta t, 2 times square root of alpha times t, sorry, that didn't render very well, overestimate or underestimate the rate of heat transfer from the wall? Okay, all set? All right, so let's see. All right, so we're split. So the correct answer is our approximate model will underestimate heat transfer. Okay, so let's think about why that is the case. So if I draw a temperature profile here, let's pick a position here, and I draw a temperature profile. The actual temperature profile is going to look something like this. What is the approximate model that we've developed, this one here? Where did that come from? We're using a resistance model. So our resistance model is going to say, well, my temperature is approximately like this, right? I've got some linear relationship. So look at the slopes here at this position. This slope is less than this slope. Right, so the actual heat transfer, the gradient dt dy, is steeper in the actual case than it is in our approximate case. So the approximate model underestimates heat transfer. Okay, I think there's been some confusion about that. Makes sense to everybody? Any questions on that? Right, another way of, yeah, I could draw it this way, right? This, we're saying this is our temperature profile, this is t, this is coordinate y. This is the actual, but our approximate model said, right, this is our delta t. The resistance is based on a linear profile, so the approximate model underestimates heat transfer. Okay. So let's then move on to the thing we're actually doing here, which is how do we figure out ways to take this approximate model apply it here and understand how to maybe simplify stuff. So what we're going to do is called an order of magnitude analysis. So we're going to use this notation O, where O is of some argument. We're going to look at the order of magnitude of the terms that are involved here. And based on the order of magnitude, then we could say, okay, this term is maybe not important. So right off the bat, starting with continuity, looking at this, we would say, if I throw away, say, du dx, then that means the entire equation goes away, right? And that's actually not what we're trying to do. So the continuity equation is pretty simple. What we're going to do is just use this to understand the relationship between u and v, but we won't be able to throw anything away from continuity, right? Because otherwise we would just throw the entire equation away. So let's start by taking the order of magnitude of each of these terms. So I'm going to say the order of magnitude of this and the order of magnitude of this. So how do I estimate the order of magnitude? Well, I would say order of magnitude of the one on the left would be, what is the change in velocity? Well, that's approximately u infinity. What is the change in x length as we go out? Well, that would be, I guess we'd call that L. So my order of magnitude for the first term is u infinity over L. I can estimate the magnitude that way. On the right-hand side, I have dv dy, so that's order of magnitude. So numerator will come back to, denominator is going to be delta, right, my boundary layer thickness. What is the numerator? Well, the numerator's got to be some velocity in the y direction. We haven't really talked about it yet, but let's call that velocity in the y direction v sub delta. So we know there's got to be some, by continuity, there's got to be some velocity in the y direction. And we'll call that v sub delta, so v sub delta over delta. Okay, so we can now just use this to understand the relationship between, between these different terms. Specifically, what I might want to look at is figuring out how large that v sub delta is. Is that going to be a really significant velocity? Well, if I just relate these equations, I would say v sub delta is approximately equal to, just solving for v sub delta, that's delta over L times u infinity. So there's a few assumptions that we need to maybe document to help us contextualize this. The assumptions are as follows. So we're going to say that delta m and delta t are much less than the length scale L. That sort of makes sense, right? You have the boundary layer. The boundary layer tends to be much thinner than the length of the thing that you're modeling. Let's also make the assumption that the Reynolds number is much greater than 1. And it's the Reynolds number with respect to characteristic length L. So I'm going to write it RE sub L. By the way, you're going to start seeing this where I write Reynolds number, and I will no longer just write Reynolds number, hopefully. It'll be Reynolds number sub whatever the characteristic length is. So if it's x, it'd be REX. If it's L, REL, and so on. So with these assumptions, what can we conclude about the relationship between the y component of velocity and the x component of velocity? We can say that the y component of velocity is very small. Right, so we would say, how would we write that out? Yeah, we would just say v sub delta is much less than u infinity. So I guess that's a useful conclusion. You can imagine, when it comes to the momentum equations, that knowing that these velocities are very different may help us. But for now, we can just say, yeah, I really care a lot about what's happening in the x direction, maybe not so much in the y direction in terms of velocity. Okay, so that's the continuity equation.